With all the silly names and invisible particles in the subatomic physics world, it can be a little confusing to get a grasp of things. I'm going to help you with learning particle classification and understanding which interactions can take place and which can't. Make sure that you stick around to the end of the video when I'll give you one final check that you should do to see if a particle decay is possible. Before I get cracking, I do need to point out that there will be some points where I trivialise some rather complex topic areas to simplify our understanding. This is needed for us to understand the basics, and should you want to go into more depth beyond what is required for A-level, then I'd love to hear from you in the comments. I'm going to look at the classification of particles, fundamental forces, exchange particles, and then look at particle interactions. I won't be looking at Feynman diagrams, the half-life of particles, or pair production and annihilation in this video. Let's start off with our vocabulary. Fundamental. Fundamental means it's a starting point, a building block if you like. An electron is considered fundamental as we can't break it down any further. A proton is not fundamental because, as we will see, it can be broken down into 3 quarks. Antimatter. Antimatter is the same as regular matter in terms of mass. When it comes to other properties, if they can be opposite, then they are. For example, an electron has a charge of minus 1.6 times 10 to the minus 19 coulombs, and so an anti-electron has a charge of plus 1.6 times 10 to the minus 19 coulombs. Most antiparticles don't have a special name. For example, the antiproton is just called an antiproton. The anti-electron, however, does, and you will come across this particle more often than other antiparticles. The anti-electron is called the positron. The Standard Model. The Standard Model is the theory that describes fundamental particles and the 3 forces of interaction between them. It is a model and has proven very useful in predicting the existence of particles, notably the Higgs boson. It does, however, have significant limitations. It can't explain the theory of gravity, including general relativity. It can't explain why there's more matter than antimatter in the universe. It can't explain the rate of universal expansion and dark energy. Right, with that bit of vocabulary out of the way, let's take a look at the classification of matter. And just to be clear, by matter, I mean stuff which exists in space and time and has mass. We are already familiar with an electron. An electron is part of a group of particles called leptons. Leptons are fundamental, and here are 3 that you need to know. Note that they are all negative, and we have the electron, the tauon, and the muon. These 3 particles also have associated antiparticles, which are positive. Each lepton also has a related neutrino. Neutrinos have a very small mass and no charge, and so rarely interact with matter and are very difficult to detect. They are abundant in the universe. This table shows the neutrinos that you should be aware of, which include the electron neutrino, the muon neutrino, and the tauon neutrino. We can denote the antiparticle with a bar above. All leptons have a lepton number, and here is a table of properties that you need to know. I've not discussed spin, but as you go beyond A-level, the spin of these particles becomes an important property to consider. The other main class of matter to consider is the hadrons. Hadrons are not fundamental. They are made up of smaller particles called quarks. We split the hadrons into 2 smaller groups. One is the baryons, which is made up of 3 quarks, and the other is the mesons, which are made up of 1 quark and 1 antiquark. Before I look at baryons and mesons, let's take a look at the quarks themselves. The different quarks are known as different flavours. There are actually 6 different types or flavours of quark, but you only need to know about 3. These are the up, down, and strange quarks. Each of these quarks has an associated antiquark. Here is a table of properties of these quarks. The 2 properties that you need to consider are the charge and the strangeness. Strangeness is just a physical property, a bit like charge, and it helps us explain how particles interact, a bit like charge. You actually need to know nothing more than that about it, except that, like charge, it needs to be conserved in certain circumstances. By considering a familiar particle, a proton for example, we can see how we would make up a proton out of quarks. By combining two up quarks and a down quark, we get a charge of +1. The proton is not strange, and so this is the only combination that works. It's made from 3 quarks, so it must be a baryon. Similarly, the neutron is made up from an up and 2 down quarks, giving it no charge, and making it also a baryon. The other baryon that you may come across at A-level is a sigma particle. These are strange particles and so contain a strange quark. The group of hadrons called mesons may contain particles that are less familiar to you. You need to be familiar with pions and kaons, which are sometimes called pi mesons and k mesons. Both of these particles can be either positive, negative or neutral, but they all contain 1 quark and 1 antiquark. That's what makes them a meson. Kaons differ from pions because they are strange particles. Here are some examples. Hopefully you can see from this that one of the peculiar characteristics of mesons is that they can be their own antiparticle. Take a neutral pion for example. The anti-neutral pion is still a neutral pion. So now that we've looked at the main types of matter, the hadrons and leptons, let's take a look at the forces that can act on them. Here you see a table with the 4 forces. They are in order of their strength. See how weak gravity is. Also pay particular attention to their range. Both the electromagnetic force and gravity have an infinite range. The weak nuclear force has a short range, showing that particles need to be in close proximity to experience the weak force. The strong nuclear force only has a range that is similar to the diameter of a small nucleus. In the table you will also see the exchange particles, which I'll come on to next. Before we move on though, we should also mention that the electromagnetic force only affects particles with charge. The weak interaction affects all particles, and the strong interaction only affects hadrons, particles that are made up of quarks. I'm avoiding the temptation to say gravity only affects the particles with mass, but that would be a fair assumption really for this conversation. The weak interaction is the only one that can actually change quarks from one flavour to another flavour, or change any particle really. Exchange particles are virtual particles that carry properties between 2 particles during an interaction. They also carry momentum over a given time and so are considered to be force carriers. You remember from Newton's second law that force is actually the rate of change of momentum. They are too short-lived to be observed and so they're said to be virtual. If we want to be pedantic, then we shouldn't really think of them as particles at all, but by doing so, they are a simplification that helps us illustrate interactions. During the different types of interaction, different particles are used. The exchange particles here can also be called gauge bosons, which are particles that exchange a force. The strong nuclear force has an exchange particle called a gluon. The weak interaction has the W and Z bosons. The electromagnetic interaction has the virtual photon. We've already taken a brief look at the strength of these forces. Gravity is so weak that we've not detected an exchange particle for it, but if it does exist, we would call it the graviton. I don't want to go into this any further because uniting the theory of gravity as described by general relativity with the worlds of quantum and particle physics is proving incredibly difficult and is the source of a lot of debate amongst theoretical physicists. The exchange particles can adopt properties that they are exchanging between other particles. This is most notable during the weak interaction, when the type of exchange particle is decided by the charge being transferred. You will need to choose between the W+, the W-, and the Z0 bosons, depending on whether you're exchanging a positive, a negative charge, or no charge. We'll have a closer look at this now as we look at particle interactions themselves. When particles interact, they need to obey some rules. Here are the ones that you need to consider. Charge is conserved in interactions. In other words, you must get the same total charge out as you put in. Baryon number is conserved in interactions. This means that if you have a baryon to begin with, then you need a baryon at the end. Likewise, if you don't start off with any baryons, then you can't finish with any. Technically, you could finish with a baryon if you also finished with an antibaryon as well, to sort of cancel it out. As well as the baryon number being conserved, the lepton number is conserved in interactions. It has to be the correct type of lepton too. I'll explain this with an example shortly. Finally, in strong interactions, strangeness is conserved, but not necessarily in weak interactions. It's common in exams for you to be asked to identify the type of reaction, and if strangeness is not conserved in the interaction, then that's a giveaway that it's a weak interaction. Let's look at some examples. Here I have a neutron that decides to decay into a proton. It's worth noting that protons are the most stable baryons, and so this is a perfectly reasonable thing to happen. Firstly, let's check that charge is conserved. We can see that there's no charge on the left side, but there is a positive charge on the right side. So charge is not conserved. I need to make the total charge 0 on the right hand side, and I can do that by adding an electron. Now the total charge is 0 on both sides. You may recognise this as beta decay, which you may have studied at GCSE. Secondly, I'm going to check the baryon number. There is one baryon on the left hand side and one baryon on the right hand side. There's no problem there, baryon number's conserved. Thirdly, I'm going to check the lepton number. I have no leptons on the left, but I do have a lepton on the right, so the lepton number is not conserved. To make the total lepton number 0 on the right, but not change the charge, I need to add an anti-neutrino. Types of neutrino stick together, and so this will be an anti-electron neutrino. One way to think about this is to split the lepton number into different types and just check that the electron lepton number is conserved, along with the muon lepton number and the tauon lepton number. The beta decay is due to a weak interaction. That's the only way that quarks can change, so it's the only way that a proton can turn into a neutron. And so strangeness does not need to be conserved, although it is in this case. Before I give you my last top tip to check to see if a decay is possible, let me just take a moment to remind you that I've put together some questions to go with this video, along with answers. They're all free and they're downloadable from, I'll leave the link in the description, but they're all available on my website. Please also take a moment to like and subscribe to this channel if you found this video useful. It'll encourage me to keep going and produce more resources. So my top tip for checking to see if particle decays are possible is check the energy and the mass. Of course, mass does not need to be conserved. Einstein told us that energy and mass should be considered interchangeable. Rather than looking at the mass of the particles, look at their rest energy. The total amount of rest energy of the particle plus its kinetic energy before any decay cannot be less than the total kinetic energy and the rest energy of the particles after the decay. So if an interaction seems to obey the conservation laws, but you're still not sure, just check the energy to make sure it is possible.